Howdy, everyone. Apologies for the late start and for the poor lighting conditions. I forgot to turn on my office lights. Personally, I hate fluorescence, so this is usually the lighting level that I prefer in my office. But anyway, so yeah, like I said, welcome back to the channel. Howdy, Judy and Georg. I'm glad you're with me today. And today we're going to be talking about, or I'm going to be going into the atmospheres of the other terrestrial worlds in a little bit more depth, specifically going into Venus and Mars. They're talking about those particular atmospheres, because when it comes to Mercury and the Moon, really they're just kind of boring, to be honest with you. They're very simple, and so there's really not much to say on that subject. But before I get into all that, what I want to do is just a few kind of announcements. Nope, that's not what I'm looking for. Okay, so for those of you, some of you who follow the channel might in fact know that we have a talk series, as it were, here at George Mason University called Evening Under the Stars. And this has been happening over the course of the semester on Tuesday evenings, sporadically. Like I said, over the course of the semester. And tonight is our last one. And I'm particularly excited about this one because it deals with, let me pull this over here. The talk is about the Mars Perseverance rover. Yeah, it's a bit dated, as it were, because Percy landed back in 2020. But Dr. Swati Mohan, who works for JPL, she was essentially the voice of the Perseverance rover. So if you actually watch the live broadcast of Percy landing, the play-by-play, as it were, was given by Dr. Mohan. And I saw this talk. She gave this talk for the Northern Virginia Astronomy Club, and I loved it. It is, and particularly if you are someone who is a fan of basically engineering, you're really going to get a kick out of it, because to me it was amazing. Just so for, I think it's 5 minutes. For 5 minutes, this thing was completely automated. It had basically a script that I ran through of different codes and different procedures in order to land safely. And it did so basically through analyzing information, sensor information. So it was essentially autonomous. And the fact that they could do this, it really just blows my mind. Or that they did this, and presumably will do this in the future. So I highly recommend watching this talk if you can. Here's for those of you who, obviously are not in the DC area, there is a Zoom link which you can use to get on this. I posted it in the comments as well. If I were on YouTube, maybe I should pin that comment. But for the website itself, the website is, I'll post this in the comments. So the event starts at 7 p.m. Eastern Daylight Savings Time, or as you can see here, 4 hours UTC, or UTC minus 4. Howdy, Charlie. Yeah, if you happen to miss the talk, then I will be, over the summer, I plan to basically clean up my channel a little bit. I plan on uploading a lot of videos that I've been, particularly science talks like this, that I've been kind of putting off the back burner. But for those students who may be watching this today, I've also posted the Discord about this. This event can be used to complete the extra credit assignment visiting an observatory. Because after Dr. Mohan's talk, we're also going to be doing a observatory tour. And because it is basically cloudy and slightly rainy today, it is going to be a closed dome tour, unfortunately. So really, we won't be able to open up for the skies, but you will see, experience the same thing folks will experience here, where we will just talk about the telescope and they will get to see it in person. You will obviously get to see it virtually, and we will just run through images that we've taken, science that we've done, so forth and so on. And so, real excited about that. Real excited about the evening under the stars today, and of course, it will be emceed by yours truly. If you haven't, like I said, if you have any questions about that, please feel free to put it in the comment or put it into the comments after. So, without further ado, one minor thing. If you're following the channel, you may have seen a video I posted a 3 days ago talking about going to Vivaldi, Texas. I put in a call in to the superintendent of the Vivaldi school system, and I have asked for an appointment. So hopefully they will get back to me. If not, then I will just pester them until they do. And really, I just kind of want to, and I'm also having a meeting with my director tomorrow, Dr. Peter Plavchen, and we're going to basically discuss, I would imagine, the logistics of how the department can help make this happen. So, all righty then. So this is the atmosphere of Venus and Mars, but again, I will be touching on the atmospheres of Mercury and the Moon. But as I said, they are pretty simple. They are pretty boring. Way out in the country, probably way out in the country near me, there's a tiny observatory. It's probably, if I had to make a guess, it's probably a private observatory, much like what Bob the science guy has. Who, if you don't know, Bob the science guy, I don't have his link to the channel. Maybe Judy can put it in there. But Bob the science guy is he does a lot of work with active observing with his great rig. He has a couple of different telescopes. I know one of them is I think one of them is a 12-inch Schmidt-Cassegrain, but he just recently bought himself a dome through donations from Patreons. And so he's got a little tiny observatory out there, the Bob's Observatory. And so, yeah, I highly recommend going over to his channel, support what he's doing. And yeah, he, like I said, he is constantly on live streaming the views that he gets from his telescope. Right now, I think he is mainly concerned with looking for asteroids, which is a very noble goal. All right, so now first question is, does the Moon and Mercury have an atmosphere? Well, as it turns out, they do, but they primarily they are entirely exospheres. So if you remember from the last lecture, when I talked about the layers of the Earth's atmosphere, the topmost layer and the most rarefied, the atmosphere, part of the atmosphere that has the fewest particles, has the fewest or the smallest density of particles, is the exosphere. And the exosphere is primarily composed of ions with maybe some neutral hydrogen in there somewhere, in a few things. In terms of the Mercury and the Moon, these, like I said, these are exospheres. These are almost exclusively negative ions. And these exospheres survive or persist over time because they are constantly being refreshed. And the way they are being refreshed is through a process called sputtering. The idea here is that you have micrometeorites slamming down. Thank you, Judy. Shamrock Bank Observatory. That's Bob the Science Guy's YouTube channel. Again, I highly recommend checking it out. Now, with these atmospheres are constantly being replenished, or these electrons are constantly being replenished through micrometeorite bombardments. And so Again, if you remember from a few lectures ago, I mentioned that the solar system has a lot of debris in it, and the vast majority of that debris by number is microscopic or microscopic meteorites, or microscopic meteors rather. These are silicon grains that are on the order of 1 millionth or 1 micron, 1 millionth of a meter or 1 micron. And what happens is when these things hit the surface, the energy they release in that impact will go to ionizing the atoms of the soil. And so the electrons in the outermost shells of these minerals, they get ejected out into space, and this is called sputtering. And so these electrons will get emitted out or get shot out into space. They will, for a while, get trapped by the gravitational influence of both the moon and Mercury. But particularly in the case of Mercury, as you can see on the right, it is highly deformed by the solar wind. The solar wind is also composed of charged particles, and they will essentially latch themselves onto the charged particles within the exosphere of Mercury, and they will blow it out. And so that's why the atmosphere of Mercury appears almost comet-like, because of the fact that the sun's radiation, the solar wind is literally blowing away the Mercurian atmosphere. Now, we also have seen, and this is true. This is definitely true on the moon, and we have the Indian Space Agency, which I don't remember the name of, but we have the Indian Space Agency to thank for the most recent observations of this. We know that there is ice, frozen water ice, in the polar craters. So we have so the temperature. These are craters in which the sun really never shines, and so they continually stay cold enough for water to stay in a frozen state. If there were, say, ice developing on the dark side of the moon, as it were, it is rotating, albeit very slowly, and eventually what might be the dark side right now is going to be the bright side later, say in the new moon phase, for example. The opposite side of the moon is going to be fully illuminated by the sun, and any ice that may have formed in the previous parts of the orbit will melt. But in the ice caps, or in the polar regions, there are craters that are deep enough that the sun's rays never make it to the bottom, and so they stay cold enough for ice to exist. And we believe this is possible on Mercury as well, but Mercury is not as well studied as you might imagine as the moon. Mercury kind of gets a bad rap because, I had a department chair who actively asked a person who was a part of, I believe, was the Messenger probe, the probe that was sent to orbit Mercury. My department chair, Dr. Dermott, straight up asked the guy, why bother? Why bother spending this money to send a probe to Mercury? We all know that it's essentially a chunk of iron and rock, which to me was doubly ironic in that Dr. Dermott's field of study was solar system dynamics. So he was very much interested in how solar system bodies interacted with one another gravitationally. So I found that to be a bit odd. But my point being is that Mercury is not well studied, particularly of the 4 or 5 terrestrial worlds. So we don't know for certain whether or not frozen water ice is on Mercury, but considering there are so many similarities between Mercury and the moon, it's probable. So what about Venus? So Venus today, as I mentioned before, is on the surface, or on the observable surface in the visible light, is a dense cloud region, which of very fast winds, which are circulating around the planet. They're very dense. They're optically thick, so that you cannot penetrate them using your naked eye to actually see the surface. When we penetrate that atmosphere through radio waves or radar, and through the 2 Soviet probes that actually managed to get down there, what we find is a world that is completely barren. There is no water. There really are no, there's no water. There's no life. There's nothing of that nature, and everything is very sharp in the sense that the very high velocity winds that we see in the upper atmosphere, we do not see the lower atmosphere. The lower atmosphere you're talking about, we believe that the winds are maybe 5 kilometers per hour at most. So there's not a lot of erosion. There's a lot of volcanic activity going on down there, and it is exceedingly hot due to the massive amount of greenhouse effect that is occurring due to that vast envelope of the atmosphere. So the atmosphere is primarily composed of carbon dioxide, 96.5%, and its surface temperature at the surface is roughly 90 times that of the Earth. Because of its slow rotation, its rotation is only about 270 odd days. Its actual rotation is slower than its year. There's very little Coriolis effect, but it is rotating, so there is at least a couple of Hadley cells that are set up. Howdy, Clive. And as I said, these winds are very, very fast moving, going anywhere between 300 to 700 kilometers per hour. And why that is not well known. I suspect that as far as I understand it, the energy that is driving these winds comes from the extremely hot surface temperature of Venus. But how exactly it's powering the winds in terms of getting it to go in one direction or another, particularly given the slow rotation of the planet, that's very much of an open question. Alien factor, maybe it might be aliens on Venus. Who knows? There was the Welsh found a particular element in the Venusian atmosphere that is linked to biological emission. So there might be life on Venus, but future studies is pretty much kind of saying no to that particular element is in fact geologic in nature. So who knows? There may be factors. I have signed an NDA that I cannot disclose if there are in fact aliens down there. There may be. The atmosphere of Venus is, as I said, highly reflective. Its albedo is roughly around 70%, 75%, meaning that only 25% of the incident solar radiation that hits Venus actually penetrates this thick cloud layer and reaches the bottom, reaches the surface to power, which then in fact powers the greenhouse effect. So this illustrates just how powerful the greenhouse effect is in the fact that you don't need a whole lot of solar radiation for things to become wildly inhabitable for that reason. And on top of that, Venus has a fair amount of sulfuric acid in its upper atmosphere, and this sulfuric acid exists as a vapor, but it also exists as liquid. And so we found that there is in fact sulfuric acid rain, which travels from the sort of upper, not from the surface clouds, but kind of upper region through the middle region of the Venusian atmosphere. None of the sulfuric rain actually reaches the surface because the pressures and temperatures are such that the sulfuric acid changes phase back into a vapor, and then eventually gets disassociated and destroyed entirely. So here's what we have in terms of the Venusian atmosphere. It is very, very simple. As you saw from the Earth example, when we looked at the Earth's atmosphere in terms of the temperature profile versus altitude, we had a couple of temperature inversions. We had one at the beginning of the stratosphere, another one at the middle of the stratosphere, and another one at the basically in the beginnings of the thermosphere. So it was a zigzag sort of pattern. So the temperature variation as a function of altitude was fairly complex on the Earth. In terms of Venus, not so much. You have essentially one temperature inversion. And again, what I mean by that is where the trend of temperature versus altitude goes back on itself. So we can see here through the troposphere, which is much higher than, or much larger than it is on the Earth. For the Earth, it's only about 10 kilometers in size, 10, 20 kilometers in size. For Venus, it's actually around 100, so it's roughly 100 times the size of the Earth. And so you have so like the Earth, the temperature will decrease with altitude. But once it gets past the troposphere, you basically get into kind of a mixture of thermosphere, exosphere, and it just kind of ramps up as you get further. But again, as you can see from the far side, in terms of pressure, as sort of a proxy of density, it is much less dense, much less dense as you get to those kind of atmospheres. And you can see some of the constituents of basically the sulfuric acid. So where it says sulfuric acid haze, this is really where that sulfuric acid rain exists. You can see that in order to have a surface temperature to experience the same amount of pressure as you are right now, you would that would exist at 50 kilometers. You would still be 50 kilometers off the Venusian surface in order to, and then at that point you would experience the same pressure as you do right now. So, like I said, the cloud layers are huge, and they are exerting a tremendous amount of pressure. So how did Venus get so hot? Well, ultimately, the reason why Venus got so hot is obviously the direct cause is the greenhouse effect. The secondary cause, or the cause that led up to it, is its position in the solar system. The key component in this story is water. Because when the terrestrial atmospheres, as I've talked about a couple of times before, they had the primary hydrogen helium atmospheres. Those were quickly lost due to thermal escape, and they were replaced through volcanism with nitrogen, oxygen, and most importantly, carbon dioxide atmospheres. In the beginning, these carbon dioxide atmospheres, where? Okay, thought I had it in here, a slide for it. And initially, the carbon dioxide levels were far higher than the nitrogen or oxygen and other metals. And as I said before, the carbon dioxide is very good at absorbing visible light, or excuse me, very good at absorbing infrared light or heat and trapping it near the surface of the world. We see this through geologic studies on the Earth back hundreds of millions of years ago, if not billions of years ago. We see that the carbon dioxide levels were extremely high, much higher than they are now, even far higher than even what we see today with the rising CO2 content due to climate change. The issue or the main difference between why the Earth looks the way it does now, does not have that massive envelope of carbon dioxide atmosphere that Venus does, is that during this time, Earth was far enough away from the sun that at the surface water could exist, even with the greenhouse effect, even with the amplified greenhouse effect of the CO2 in its atmosphere. Water could exist in a liquid state on the Earth. It could not on Venus. At no point in the Venusian history was water able to exist. And water is an essential sink for carbon dioxide. It is essential for what we refer to as the carbon cycle, where carbon dioxide gets recycled through the Earth's biosphere. It is in the atmosphere. It then gets absorbed by certain minerals, becomes limestone through the aid of water, or gets absorbed by water. Gets absorbed by water, and then that basically gets interacts with the minerals on the bottom of the ocean or lake or what have you. That turns into limestone. Volcanic action will then release that CO2 back into the atmosphere through volcanic eruptions, underground or undersea vents, that sort of thing. So for the Earth, we see a marked decrease in the CO2 content of the Earth due to this presence of water. We do not see that for Venus. And so Venus has what some would call a runaway greenhouse effect. And it's kind of a misnomer to call it a runaway greenhouse effect because Venus was really never in a situation where the temperature was cool. For a runaway greenhouse effect, that's more of a terrestrial or Earth-based idea, in that you have a relatively cool surface with a relatively thin atmosphere surrounding it, and then due to an imbalance of greenhouse gases, you have a compounding effect of the more greenhouse gases you have, the warmer the world becomes, the less water exists in a liquid state. And then that means that there is less carbon dioxide or less greenhouse gases that are being absorbed, which keeps them in the atmosphere. But carbon dioxide is still being emitted off the surface. So more carbon dioxide, more greenhouse effect, less water, and so forth and so forth and so forth. And then you have this runaway greenhouse effect, and the planet burns. For Venus, there really was no starting point like the Earth. It really just was a massive greenhouse to begin with. So let's move on to Mars. What is Mars like today, and why did Mars change? So Mars today, as I've mentioned before, is a somewhat of a provocative world in that it might, Clive, have alien life on it. It may, in fact, have had developed alien life at some point in its past history, because Mars has geologic features which are very, very similar to geologic features that we have on the Earth, particularly geologic features which involve the presence of liquid water. But today it's a barren world. We believe that it is covered in primarily iron oxide dust, which is why it's the red planet. It is literally coated in dust, or literally rusted. And beneath that is some kind of a permafrost of water ice underneath it. So we're fairly certain that there was liquid water on the surface of Mars at one point. Where did it go? Oh, and I should also say that the atmosphere of Mars, very much like the atmosphere of Venus, is primarily composed of carbon dioxide, but to a much, much lesser extent. Now, I've got to hawk my own astrophotography, as it were. This slide deck is a bit old, and so back August of 2003, we had the closest approach of we had the closest approach of Mars to the Earth for tens of thousands of years. Mars has never been as close to the Earth as it was on August 26, 2003, and it won't be again for another 10, 50,000 years or what have you. The reason for this is because both of the orbits of Mars and Earth are ellipses. You have a perihelion and aphelion for both orbits. There are positions where the Earth is closest to the sun. There are positions where the Mars is closest to the sun. So what we had in this situation was that Earth was as close as was pretty much near aphelion. It was pretty much as farthest away from the sun as it was ever going to get. And Mars was near perihelion. It's perihelion. It was as close to the sun as it ever was going to get. And so it allowed us some unprecedented views of Mars. And so on the right is the Hubble image of Mars, a classic Hubble image of Mars. And on the left is what I could accomplish using a 24-inch telescope at Emory University on that day. And really what this is actually a still frame from a video that I took of Venus at that time. So this is actually not processed. And so I should go back and see if I could, well, I don't have the calibration frames. I don't know. Maybe I could touch it up. But you can definitely see, these are inverses of each other. So the dark region, I don't know if you can see my cursor, but the dark region off to on the left of center for my image is the sort of dark region on left of right of center on the right. And hopefully you can kind of see the on the Hubble image, there's a dark mountain range or dark terrain, linear terrain, and kind of see it on the other side. And so maybe. So yeah, that's the difference between having a relatively small telescope on the Earth and a telescope in space. So yeah, go space telescopes. The Martian atmosphere this was a slide I was looking for. The Martian atmosphere is really a fingerprint of, or a synopsis of, not synopsis, a representative of what the atmosphere of both Venus and Earth looked like at the early points in its history. And so the atmosphere is primarily composed of carbon dioxide, in this case 95%. You have a significant amount of nitrogen, you have some oxygen, you have some argon. But again, we have to keep in mind, no, Judy, I did not, in fact, use a P900. I don't know if P900s had been invented yet. I certainly was not aware of that technological marvel at the time, but who knows? Maybe I could buy one and set it up with a 32-inch. See what we get. I'm actually kind of half serious about that idea. Anyway, but I would go with the P1000. I mean, you can't, if you're going to do this, you can't skim. So this is what we refer to as what's the word I'm looking for? Primeval or the primordial atmospheres of these terrestrial worlds. If you have, and like I said, in the case of Venus, there was no water, so that carbon dioxide, there had nowhere to go, so it basically just stayed there. For the Earth, the carbon dioxide got leached out of the atmosphere, leaving a primarily nitrogen, oxygen, argon mix with some carbon dioxide left over. And then here we have a very tenuous atmosphere of also those constituent particles. Again, this is another graph of showing the compositions of the atmospheres of carbon dioxide, nitrogen, and oxygen. You have Mars, Venus, and the original Earth, or the primordial Earth, and then you have Earth now. So this is this carbon dioxide atmosphere, carbon dioxide, nitrogen atmosphere, we believe to be basically ubiquitous for any terrestrial world. So if we find a terrestrial planet, exoplanet, out in the universe, more likely than not, depending on where it is in its orbit, if it's in the habitable region, then we would not expect that the atmosphere is primarily composed of carbon dioxide. We would expect it to be primarily composed of nitrogen. If it's not in the habitable zone, then then we would expect more of a primordial atmosphere. So this is one of the ways that astronomers, particularly those with JWST, who can now start studying exoplanetary atmospheres, this is one of the ways that they're going to try to find planets that are habitable or might in fact have life on it in one way, one form or another. Hey, my observatory is here. Um, Hi, Observatory. How are you? I know you're being rained on at the moment, so, well, drizzled on, I guess, but thank you for being here. Um, that is obviously a little weird. Um, so, so what happened with Mars? Why is Mars the way it is now? Yes, Observatory, it is cloudy, and it will probably remain so for the rest of the night. Um, so what happens is that, and I think I'm getting ahead of myself here. Yes, I am getting ahead of myself here. So what happened with Mars? Well, the reason why Mars is the way it is that two things basically contributed to its demise, as it were. The primary thing is that it is small, because Jupiter cleared out a lot of the material that was around Mars when it was forming. Mars's growth was stunted, and so Mars is only roughly half the radius or half the diameter of the Earth, and so, roughly speaking, half the mass. Certainly, the mass is not high enough that it can hold on to reasonably excuse me reasonably rapidly reasonably fast nitrogen molecules and oxygen molecules. Um, these thermally escaped over a much shorter time scale than on the Earth. The other issue is that Mars was slightly. Oh, howdy, Blue. Mars is slightly further away. Obviously, Mars is slightly farther away from the Earth. Well, 1.5 times the distance from the Earth, and so it's colder. And so both of these contribute to the fact that the atmosphere of Mars dissipated probably around, or for the most part, around 1 billion years or so ago. We expect that to be the end of the era upon where liquid water existed on its surface. In terms of seasons, Mars has a fairly eccentric orbit, particularly in comparison uh, to that of the Earth or Venus, for example. And oddly enough, as sort of a trick of uh, a cosmic coincidence, the axial tilt of Mars is very, very close to the Earth. The Earth and Mars, roughly speaking, have about a 23.5 degree axial tilt. As we'll find out with Mars, that is indeed a cosmic coincidence. But in comparison to the Earth, it also has a slightly more elliptical orbit, meaning that the seasons on Mars are a little bit more extreme than you would find on the Earth. The atmosphere, like I said, is primarily composed of carbon dioxide. Now, unlike any of the other terrestrial worlds, the atmosphere is primarily, so for the Earth, I talked about the carbon cycle and the fact that the Earth's atmosphere is slowly leaking out into space because the Earth does not have a absolute container. It is slowly leaking out into space, but it is constantly being replenished by volcanism, by geologic activities. Carbon dioxide, nitrogen, and so forth is being spewed out into the air from trapped elements inside the Earth. Howdy, Tina. For Mars, Mars's atmosphere is being replenished, but in a much different way. The Martian atmosphere is a consequence of its ice caps. So you have on the northern and southern caps, you have ice caps that are made of dry ice or carbon dioxide. Under the northern cap, we believe that there is in fact a smaller cap or subcap, I guess, or undercap composed of water ice, and that the dry ice is shielding it and causing it not to sublimate. But the dry ice does sublimate. So in the summer, in the northern hemisphere, that northern cap sublimates, shrinks noticeably, and that carbon dioxide gets released into the atmosphere, gets held on by the weaker gravity of Mars, and then gets circulated due to its rotation around the surface. And then when winter comes back, then that carbon dioxide gets basically sucked back into those polar caps and freezes again, and the polar caps get much larger. So the atmosphere of Mars is very variable in terms of its density. In some cases, it's comparatively more dense when it's summer in the northern hemisphere, and then less dense when it is in the when Mars is in winter in the northern hemisphere. And so here you can definitely see the contrast of what I'm talking about. These are HST images or Hubble images of Mars taken from 1996 through 1997, October, January, and then March. And you have in October, you have the Martian winter in the northern hemisphere. And so you have that pole is pointing away from the sun, is angled away from the sun. You have a massive polar ice cap, again, made of carbon dioxide. And then as it progresses, you move from winter into spring, that ice cap will sublimate. Again, it's not melting, it's sublimating. It turns into gas. That gas goes and feeds into the atmosphere. And then in summer, the ice cap becomes very attenuated to the point that we only have really that water ice cap, that subcap underneath it that really exists. And then it goes through the cycle again, where in fall the ice cap will begin to grow again, and then back in winter it'll be friggin' immense. And you have a similar thing with the southern ice cap. The southern ice cap is smaller, and so when it is summer in the southern, or it is summer in the southern hemisphere, the southern ice cap will actually melt or sublimate completely. It will basically be gone. And so, yeah. In terms of, now, one of the things that's kind of strange about the Martian atmosphere is the storms that can appear on it. Now, for those of you who weren't here at the top of the hour, Dr. Swati Mohan is going to be talking tonight about the Perseverance rover. Part of Perseverance is a aircraft called Ingenuity. It's a helicopter. Now, one of the, I guess you could say, its primary reason for being is that they wanted to see if they could get it to work. Because the Martian atmosphere is so tenuous, and as we know, you need an atmosphere in order to have lift, to lift an aircraft above the surface and have it move around. They were uncertain as to whether or not the blades could generate enough lift, given such a tenuous atmosphere, to go around, to fly around. As it happens, yes, it is. Even though it is so tenuous, the blades are long enough and constructed well enough that they can generate just enough lift to fly around and actually to scout around a much larger region than Perseverance could travel on wheels. So it's awesome. Awesome little thing. But what amazes me about this are two different things. Well, first off, you can have from the rovers like Perseverance, we have images of dust devils. For those of you who have never been to the American Southwest, dust devils are when you have a very dusty environment, and you can have localized, basically kind of like a tornado, only way weaker. Is you have a circular motion of wind, it picks up the dust, and it causes it to look like kind of a mini tornado. And so we see this on, like I said, in American Southwest. It's kind of a common occurrence. And apparently we can also see this on Mars. So the atmosphere, again, is thick enough that it does have enough force, or can exert enough force, to pick up this dust, suspend it in the air, and cause it to spin. But the thing that I find to be most amazing about this is that the Martian atmosphere is such that it can create a dust storm that encompasses the entire planet and it can do so in a relatively rapid way. So here again are two Hubble images. The first one is in January 26th of 2001, and the second one is September 4th, 2001. So only a few months away from each other. And so on the left, you can see that you have clear skies. You can see Hubble could see all the way to the surface as we normally do. But on the right, for reasons I don't believe are quite clearly understood, there was enough wind action that there was enough force to pick up the surface layer rust and circulate it around the entire world. Now, something to keep in mind is that again, Mars is small, so the escape velocity, the surface gravity of Mars is significantly less than it here is on the Earth. So it doesn't take as much force to pick up dirt and spin it around and cause dust devils, or in this case, a dust storm. But the fact that it covers the entirety of the planet is what really amazes me. Something else to keep in mind is Mars's rotation, again, as a happy coincidence, Mars's day is almost 24 hours. So again, Mars has a similar axial tilt, a similar rotation than the Earth. But again, there's not a lot of winds or a lot of weather on Mars, simply because the atmosphere is so tenuous. And so you don't see or at least we don't really see a tremendous amount of differentiation in the atmosphere. We don't see easterlies, we don't see westerlies, there's no jet stream, we don't see these complicated weather features in the Martian atmosphere than we do on the Earth, which again, I believe is what really helps or facilitates this global dust storm in terms. Yeah. Austin, we should just give him the Nobel now. He has everything worked out. So yeah. Now, this is where we have to thank the moon, or we should be very, very thankful for the moon. Because if it weren't for the moon, when it weren't for our moon, we would be in a very similar position as Mars. In the sense that the moon acts as essentially a tidal brake. Its gravitational influence essentially keeps our axial tilt stable. Now, it does fluctuate about a degree and a half, and what that means is that over the course of thousands of years, or tens of thousands of years, the seasons on the Earth are going to change in their extrema. And I'll explain that in a moment. For Mars doesn't have that break. It has two moons, the potato moons, but they basically are asteroids. They have almost no mass in comparison to Mars. So the Martian axial tilt ranges wildly. It can range from 0, meaning it has no tilt, all the way to 60 degrees, and it will oscillate backwards and forwards across this. If you remember all the way back when I talked about what causes seasons, seasons are caused by primarily the axial tilt. Distance does play a factor, but all that really does is when the planet is closer to the sun, it makes the hemisphere in summer hotter and the hemisphere in winter colder. And when it's further away, vice versa. But the tilt dictates how much direct light you have on a certain area. The greater the tilt, the more, or when you have a tilt, that's going to cause certain areas of the planet to have a more direct light coming at it, and then other areas are going to have indirect light. That's how we have summers in the northern hemisphere when the northern hemisphere is tilted towards the sun, and we have winters in the southern hemisphere because the light is much more oblique or much more at an angle in the southern hemisphere than it is in the northern. I hope you can imagine that if you increase that tilt, the sunlight in the northern hemisphere is even more direct, meaning that its summers are going to be much hotter and the winters are going to be much colder because, again, you have even less sun hitting this. So when you have an axial tilt of 0, the only way the temperature is going to change is by latitude. If you're higher up, it's going to be colder because, again, you're getting less direct light. And distance. When the planet is closer, the planet overall is going to be warmer. And that's it. So the seasonal changes for a planet with an axial tilt of 0, unless the eccentricity is very high, the seasonal changes are not going to be all that great. Again, you would experience a larger seasonal change or a larger change in temperature by going north or south rather than waiting. But if you're at 60, then you have wild temperature changes. Your seasons are way more extreme. You have a very, very hot summer, or compared to a very, very cold winter in each of the particular hemispheres. And so here's an example of sort of the intermediate or regions where you have, in the bottom where you have those two major ice caps. That's in a situation where you have almost 0 axial tilt. And so again, no seasonal variations. It's only cold at the poles and it's warm around the equator. So you have massive poles that are formed. Here the carbon dioxide just gets frozen on the poles. And then as the axial tilt drops, in the upper left, you have an actual image of Mars. And it shows basically, again, in the winter, or in the summer in the northern hemisphere, you have a small ice cap. In the summer southern hemisphere, you have a large ice cap. And then if you have extreme axial tilt, you will not have any ice cap in one hemisphere, and then you'll have a massive one in the other. Martians, if Martians were to exist and talk to us on a regular basis, then I could tell you that they would prefer icier conditions. So they prefer to be near the poles. But again, I can't really tell you because I signed that NDA and I lose my $53 million a day paycheck if I really, tell you about it. So you didn't hear from me because, Martians don't exist. All right. So that's it for today. I've gone the hour. Tomorrow, I will attempt to post a lecture talking about... Actually, hold on. I can tell you. I have the schedule up. And I will be talking about, I believe, the giant planets. No, I will be talking about the giant planets. So I will go into the Jovian worlds, first starting off with Jupiter and Saturn, the gas giants, and then talking about Uranus and Neptune, the ice giants. So please stay tuned for that. Also, what I'm hoping to do tomorrow is have a live stream where I go over how you can use the American Association of Variable Star Observers to do science at home. You can do astronomy at home, and I hope to be able to show you how that's done. The AAVSO has a massive database of observations taken by citizens around the world on a plethora of different objects, eclipsing binaries, catastrophic variables. Basically, these are white dwarfs that explode every so often. Our Cepheid variables, our Lyras, pretty much any kind of variable star you can think of, they've got observations on it. And so tomorrow, what I'm hoping to be able to do is to take the classic Cepheid, the archetypical classic Cepheid variable, delta Cephei, look at its observations and derive a period from it. From those, first, I'm going to show you first, I'm going to show you what data is available and how you can access it. I will then show you the programs that are available for data analysis. I will download the data Cepheid photometry or brightness changes over time. I will show you how to derive a period using the program and that data, and then also from that you can get a distance. And I will show you how we get distances to galaxies through the period luminosity relationship. So it's a step kind of beyond stellar parallax. So I'm hoping to be able to do that tomorrow, depending on my energy level and my overall health. So yeah. Am I going to discuss Nibiru? I'm assuming that's Planet X. No, I will not be discussing Planet X in its various different forms. There was, on a serious note, just as a just kind of a minor aside, you may have heard somewhat recently, within the last 5 years or so, there was talk of an actual Planet X. In this sense, it was, I think X in this sense was the Roman numeral 10, because Pluto's a planet. And howdy, Tina. And so yeah, there were some observations of the Kuiper Belt. There were some observations of Kuiper Belt objects out there in the Kuiper Belt. And what they noticed was there was a lack of these objects in a particular area of the sky. And so the inference they made from that is if there is nothing there, we would expect material to be fairly homogeneous. We would expect Kuiper Belt objects to be all over the place, for them not to be on one half of the solar system as opposed to the other half. And so the hypothesis was, hey, if there are no KPOs, Kuiper Belt, or KBOs, Kuiper Belt objects over here, then there must be a mass out there which is bullying them away. It's throwing its weight around, and it's throwing those KBOs away. Well, I can tell you that hypothesis has been tested, basically through multiple and more in-depth observations of the blank area of space, and we found some Kuiper Belt objects out there. So as it turned out, that gap was not physically motivated; it was an observational bias. We were not finding objects out there because we weren't really looking for them. So it just happens that basically the objects out there are on whole dimmer than the ones that we see on the other side, which is still a fascinating result, because it now asks the question, why are these Kuiper Belt objects, why did they have a higher albedo than these Kuiper Belt objects over here? But I can officially tell you that we have not found another full-fledged planet anywhere in the solar system. We have a half dozen or so quote-unquote dwarf planets, but that's another story entirely. As for planet Vulcan, we have actually, and I know you're saying this tongue-in-cheek, but I am, there is some validity to this. There is actually a planet, there was a planet Vulcan. So in Star Trek lore, I believe, and I could be having the name of the system wrong, but I believe that in Star Trek lore, the planet Vulcan goes around 51 Eridani. And there was a planet going around, or we believed that there was a planet going around 55 Eridani, 55 Eridani B. And that was listed as Vulcan. Informally, it was called Vulcan. But sometime early this year, rather, more observations of Eridani B were taken, and it doesn't exist. What basically the problem is that with the types of observations that we take, in this case, radial velocity, the radial velocity signature of a planet can in fact be misinterpreted. And so instead of that signal being due to a planet going around and causing the planet or the star to shift, you have stellar activity. The star itself can pulsate or generate spots in such a way that it mimics the behavior of what we would expect a planet to look like going around. So Vulcan, in this case, is a great example of how astronomy never rests. And there are astronomers out there whose basically job it is to kill planets. We find these exoplanets, we attempt to confirm them, but we, like I said, we don't rest. We continue to look at these systems with the idea of, is it really there, or is it due to some other effect? And like with a lot of things in astronomy, we can't determine if it's a stellar effect or if it's basically due to stellar activity without more and more observations, without more and more precision observations. And so, yeah, there's an astronomer out there who's nicknamed the Planet Killer because he tries to find planets, he tries to confirm planets rather, and he doesn't seem to confirm them. He seems to unconfirm them. So yeah, he kills planets. Which, hey, somebody's got to do it. But like I said, it just goes to show, science is, we don't just say something is true, or we don't just say, hey, this is the thing, and we just put it on a shelf and never look at it again. We are constantly studying even stuff that we believe to be fairly settled science. Alrighty then. For those of you, I apologize for those of you in the beginning, but I want to reiterate that tonight we are having a public talk by Dr. Swati Mahan. She will be virtual. She is at JPL in California, and she will be remotely giving a talk tonight. It will be 7 p.m. Eastern Daylight. It'll be 4 p.m. for her, and then it's UTC -4. Now the UTC is 11 p.m. She will be giving a talk, like I said, remotely, talking about the Perseverance rover. And this, I know it's a little dated, but I've seen this talk before. It's fantastic. It goes over just the Herculean feat of how they constructed this vehicle and programmed it so for about 5 minutes, it was not being controlled at all. It was operating autonomously. And it did so during the most dangerous part of its landing sequence. And so she will go over how that was done. And like I said, I was blown away by that talk. I don't mean to overhype it, but I highly recommend if you are around to see it, please do so. I've put the earlier in the chat, I've placed the Zoom link, which you can find on the website. It's located here. It's free. You just hit the Zoom link and show up and watch the talk. Also, somewhere in here, I also put in the website that I'm showing you here. It's George Mason Observatory Evenings Under the Stars. After the talk, we will be giving a virtual planetarium, or excuse me, virtual observatory tour, because as the observatory itself told us, it's cloudy, and so it will not be open to the sky tonight. So yeah. All right, everyone. Unless there are any questions, I will bid you all good day and peace out and clear skies wherever you are, because they ain't clear here. All right, folks.